Okay, so problem one's on the screen here. So it says that two snapshots of the same pulse at different times are plotted together in the diagram. We have the diagram on the right. It's a little bit fuzzy, so sorry about that. The pulse has been reflected from the right-hand end of the string located at position R. So the first question we're asked to solve is the right end fixed or free, and explain our reasoning. So kind of what we have here is we have a sinusoidal wave pulse. So the first bit of the pulse, maybe I'll change to red. Red is a little bit more visible. First part is right here. It's just this pulse, otherwise the wave, notice over here we have no amplitude here, no disturbance here, we have no disturbance here. So it's just this little kind of single cycle, and it's moving to the left. Then at some time later, actually 15 seconds later, we're told we get something that looks pretty similar. We have kind of the same idea. It's sinusoidal, it's a single cycle, but it's moving to the left this time, we're told. So the first part we're asked is this free end? So the first thing we need to realize is that kind of the phenomenon we're dealing with is reflection, and reflection produces two different results depending on what the end of the, in this case, the string is. So it can either be fixed or free. And if it's a fixed end, this is kind of just a good thing to remember. The details of why are actually, if it's a fixed end, the pulse will, the reflected pulse will be inverted, or if inverted is hard to remember, it's just flipped upside down. And if we have a free end, the opposite happens. The pulse is upright, or alternatively, you could just say there's no flip, or it's the same orientation, that kind of thing. So what do we have here? So part of the challenge with this question is just simply picking a point to keep track of and keeping track of that. So I'm going to do, I think the easiest is the very leading edge of this pulse here. So we can figure out everything that's going on just if we keep track of this leading edge and what's happening right after it. So imagine this point kind of move to the right, and there's some point over here. We don't know if it's exactly right here, but it's at what is called XR, the point where the reflection ends up happening. This point moves here, and you can almost imagine it turns around. This is all going to be kind of in a single dimension, so it's just we're moving along X here, but it turns around and it starts moving back. So this point is always in the front, so that makes this part, this is the front of the reflected wave, so it's the same point right there. This is kind of our lead edge. So in terms of determining, has this pulse flipped? And when I say flipped, it's a little ambiguous. Inverted or upright is more clear, but flipped, and this means in a vertical sense. So what happened? The pulse is moving to the right, this leading edge, and then the pulse immediately goes negative amplitude, right? Here's the pulse, it's moving to the left, and what's the first part that, as we trace over with our pen, we have the leading point, and then it goes negative. So this pulse is, in fact, in the same orientation as the original wave was. The reflected part is just the same. So we did not have a fixed end, we had a free end to our rope because the orientation is just the same. It's flipped horizontally, it hasn't flipped vertically. I think that's the key point there. And you got to think about it. So we have a free end. Oops. Okay, part B says, where is the right-hand end of the string located? So we already kind of labeled this point XR. What we want to do is find exactly where that is on our number line. So we'll just put it over on the right-hand side here. I seem to have lost my marker, my pen. So what we're going to do, this is sort of not really wave physics anymore, which I think a lot of the problems this semester you'll realize, oh, this is just something I learned in first year. At this point, it kind of gets simplified to something a lot easier, I guess. So there we go. Let's put where we kind of just, this is some random distance off to the right. We don't know exactly where this is, but this is at XR. And let's label some of these distances. So at time equals 0, let's keep track of this point right here. It's going forward. And end up at the reflection point. So we'll call this, what I'm going to call this distance here, I'm going to call it delta x. Let's call this delta xa. And we'll label this initial point right here where we started out as x subscript 0. And the subscript will be to keep track of the time. Then the wave is reflected. Remember, we're keeping track of this point at the front of the wave pulse after the reflection. So the wave turns around and it moves to the left. And this is kind of where we catch it at t equals 15 seconds. So let's call this distance here, we'll call it delta xb. And we'll call this point where the leading kind of edge of the pulse is, we'll call that x subscript 15. So I think we labeled, and at this point it's really just leveraging the fact that if you have something that's moving with a certain velocity, the change position is just equal to the velocity times the time interval over which it moves. So let's break this down a little bit. Our change in, this is not a vector, I've just written this as a scalar, so this is just the distance that we travel, or sorry, that the wave pulse travels. It's composed of two parts. When the wave is moving to the right towards the reflection point, we called that delta xa. And then there's the second part where we're moving after the reflection has occurred, moving away from the reflection point. We can further break down what is delta A based on the way this number line is oriented. So remember, XR is going to be something greater than 12, 13, 14, 15. We want this to be a distance. We want this delta to be positive. It's just a distance. So we're going to say it's XR minus X0. And same thing for the distance delta XB. It's XR, which should be a big number, minus X at 15 seconds, which should be a smaller number. That's equal to V delta T. At this point, we're all set because what we want to solve for is XR. So we just need to do a little bit of algebra at this point. So we have 2XR minus X0 plus X15. That equals V delta T. And we should arrive at something like 1/2 V delta T plus X at time 0 plus X at time 15. That should be our final answer, and kind of just using variables, leaving them in kind of in a symbolic form. I don't think I'm going to solve this for you guys, just to kind of keep things moving and be quick. But what I'll do is I'll write over here what you guys would need to plug into your calculator to actually do the computation. The velocity is 2 meters per second. Or sorry, the speed, because we're not worried about vectors, we're just looking at distances, not displacements, that kind of thing. The change in time was 15 seconds. The initial position was at x equals 5 meters. And at t equals 15, we ended up at x equals 8 meters. So if you guys plug that into your calculator, that should give you exactly what you need, but I'm just going to leave this in symbolic form here and move on just for the sake of time. I think you'll get something like XR is equal to 21 or 21 and a bit, that kind of thing, but the details or the actual numbers not super duper important. Okay, so for problem 2 here, we have, we're told that the tension in each string of a musical instrument, so this is something like a violin or a guitar or something like that, must be equal, otherwise the instrument could become warped. Consider an acoustic guitar with a steel string. Each string is stretched to a tension of 80 newtons. The strings of the guitar are 64 centimeters long, and the density of steel is just under 8,000 kilograms per cubic meter. Furthermore, we're told that the high E string must have a fundamental frequency of 329.6. And at the end of all that, we are asked to find the diameter of the string. So the first thing that we need to kind of realize, maybe I'll do it off to the side here, just this doesn't work, get in the middle of the equations we're going to use. If we have an instrument like a guitar, the string is fixed between 2 points, one at either end of the instrument, and when it's plucked, you get a standing wave on this. So one of the key words that I didn't circle, but maybe it's so important that I'll even change color and we'll circle it, is the notion of fundamental frequency. So I think you've seen Professor DeVette drawing different modes of standing waves. When you have the fundamental frequency or you have the fundamental standing wave mode, that means that you basically have the wavelength is as big as possible. So on a stringed instrument that has kind of fixed end conditions, you get a standing wave envelope that looks like this. Or I guess you could do one solid and one dash. That's pretty conventional. So in this configuration, for instance, if we had a higher order mode, like a second mode, third mode, or whatever, you would have the same string, and you maybe have something like that. You could even have something like that. Anyways, not important. Just realize that there are more than just this option here. This is the fundamental, or the kind of the lowest order mode. So when we have something like this, imagine that you kept drawing. You could draw the rest of one repetition like this. And what you would realize from that is that in this distance, if we call the length of the string L, L is half a wavelength. So we'll use that result. If we had a higher order term, L would there'd be more wavelength that gets fit into a single unit of L. Okay, so kind of understand what our wave looks like, but we need to put together actually a lot of tools to figure out what is the diameter here. One thing you may want to consider, I think, imagine we were a little bit lost. We're given sort of a density, we're given a tension. I think you guys learned from the first kappa or one of the lectures, you have strings under tension. The wave speed along that string is equal to the square root of the tension divided by the linear density. So we have a difference now. This is a linear density. This would be in units of kilograms per meter. If you go along a line, basically if you move a meter, how much mass was in that meter. This is a volumetric density. Notice the units don't match up with what we wanted for mu. They're in kilograms per unit volume. And conventionally, this is given the variable rho, which is a Greek letter, but it kind of looks like a slanted P. But anyways, we can figure out what this is. If this is the mass per unit volume, and we want to convert into the mass per unit length, what we can do is we can write that mu is equal to the mass of the object divided by the length of the object. We're using the same capital L because our object is the string. The mass is just equal to the volumetric density times the volume, so we can replace this with a capital V times, oops, got a bit ahead of myself. Mass is the density times the volume. And now we have to ask ourselves, what is the volume of our string? Really, what you could imagine is it has some diameter d, use lowercase, and it has some length L. It's a cylinder. So all we need is we need the cross-sectional area of the circular face, and we multiply by the length. Since we're dealing with diameter, we'll leave this as a d. I know what's most customary is you write the area as pi r squared. What we'll do is we'll do pi d squared over 4. It's really just the same thing. So all I'm going to do is replace this v for the volume. I'm going to replace that with the area of the circle. And we have to multiply by the length. This is just area times length. That gives us volume. The L's cross off, which is really nice. And what we find is that mu is equal to, it's a little bit, there's a lot of terms. Pi times rho divided by 4 all times d squared. So we can put that into the equation we had for the velocity. So now we can write the velocity of the waves on the guitar string or on the violin string, whatever this instrument may be. We can write it in terms of the parameters that were given in the problem, which is nice. We don't have mu, but we have the tension. Pi is just a constant. Rho is given to us, that kind of stuff. So what I've done is I've moved the d outside the square root, and when you square root a squared number, you only have a single power left. So this is our velocity. So I bet all of you are sitting there being like, this is not useful. We're not getting any closer to the answer. But we have something with the diameter of the string, and we know something about the wavelength. The only other thing that we know that I haven't really alluded to yet is we have a wave. We know what the velocity is. We know something about the wavelength. And we're also given a frequency. So those three quantities can always be related. The speed of the wave is equal to the wavelength times the frequency. We have an equation for the speed. We have an equation for the speed. We can just set these equal to each other. So what this means is lambda f is equal to 1 over d times the square root, 4 times the tension, divided by pi, divided by rho. We don't know exactly what the wavelength is, but we have an expression for it. From all the way over here, we know that the wavelength is equal to 2L. So we can sub that in. 2L times the frequency is equal to 1 over d times 4 times the tension, divided by pi divided by rho. Square root of this 4 is 2. There's also a 2 here, so these cross off. And what we're left, we kind of cross multiply the d and the LF. I know this is a lot and I'm going quickly, but it's just algebra. It's not really physics at this point. I'm trying not to dwell on it. We get something that looks like this. So I think what I will do is I will previously, you guys have all the numbers right. Tension is going to be 80 newtons. The volumetric density is 7950 kilograms per cubic meter. The frequency 329.6. Oops. That's in hertz. Hertz is per second. So that's nothing strange. It's just like a second in a denominator. It's like meters per second without the meters, that kind of thing. I'll even convert the length into meters for you guys to make the calculations easier. Everything here is in SI units, so you just plug it in and not convert anything. So I will leave this for you guys to calculate. One thing I challenge you guys to do first, if you want, is just do unit analysis on this and check that everything kind of makes sense. So the left side here, it's a diameter, right? It should come out in units of meters or in dimensions of length. This part here, you have L in units of meters, you have F in units of hertz, which is the same as a second. So this term in front here has units of meter per second, but it's in a denominator, so that's 1 over meters per second. So you have to check out what's going on in the square root. You'll have to square root it, but you want to check that everything on the right side will end up with units of meters. Otherwise, I screwed up and the calculation will never work. But what you can do is you can put the numbers in, get the numeric value, but I'd really encourage you, because this is a pretty complex final answer in terms of what we solved in variables, make sure that you get the units to come out correctly as well. So that's your best tool if you're writing a test and you want to, if you have to do some algebra, set some equations up, and arrive at an answer. If the units make sense, then there's a high chance that you probably did the whole thing correctly. So it's a fantastic check and a good skill to build. Okay. So another instrument or music type problem. We have a xylophone, otherwise known as a glockenspiel. So we're told that it's a percussion instrument. There's keys made of different lengths. And the way it operates is a key is hit with a mallet. The key vibrates with the fundamental standing wave mode. And that mode has a particular frequency. And we're told this is really helpful. This is often one of the challenges when you're doing these problems, is to decide what your kind of end conditions are. We're told that we can treat these like strings with free ends. So notice here that there's nothing really touching these keys at the ends. So there's nothing there can be nothing constraining them. That means they're free to vibrate, which means they can be considered free. That's kind of what the rest of the sentence says. So we're told what an E note is. It's 1318.5 hertz. And the key that generates that sound, we're told, is 10 centimeters long. And again, this is the fundamental frequency. We're also told what a G is. A G is 1568.0 hertz. So the first ask is to find out how long this key that makes a G note is. So we know that these, I assume we know, hopefully you guys know. We're told that these keys, they're all, where does it say it? They're metal plates. I think it said steel. Doesn't actually tell us what metal they are, but they're all the same metal. So the speed of sound it's determined by the material that is the medium through which the sound traveled. So if these keys are all made of the same material, then the speed of sound in each key is the same as the next key. All the keys have the same speed of sound. So what this means is, imagine we have kind of the wave equation or whatever is V is equal to wavelength times frequency. We could write this down once for when you have whatever the wavelength is in the E key times the frequency of sound that we associate with E. You could also write down the same thing for a G, or the key that carries that. It has a particular frequency. But notice I've written down V in both cases, and I haven't given it a special subscript for E or a special subscript for G because they're the same speed. So because these are the same, we have two equations. They both are equal to the speed, so we can set them equal to each other. So we're kind of on our way. We're in a good place to arrive at the answer here, but we need to figure out what the wavelength is. And this is pretty typical. Most music instruments operate by making standing waves. And when you have standing waves, you can figure out what the wavelength is in relation to the geometry of the instrument. So we're told that these are in their fundamental modes, but these are different than, remember on the last one, we had this kind of fixed end conditions. We put two nodes and then have an envelope of a standing wave between them. Here we have the fundamental mode of a free end instrument. So what this looks like is you have a node in the middle, and I'm really bad at drawing this, but you have something like this. I think I made, overall it's pretty good, it's just a bit too long. That's pretty decent. So the neat thing is everything has shifted a little bit, but this is a length L, and in terms of how much of a wavelength is in here, this is still half a wavelength. So all of the counting, basically, and all the physics for a closed system is the exact same as a free system, more or less. The way that you plug numbers, you choose what a wavelength is in terms of L, it's all the same. Things start to get different when you have one end fixed, one end free, and that's what we have in kind of the last example. But again, we have the same relation, is equal to lambda over 2, or in other words, lambda is equal to 2L. And if you don't believe me, or if you're having a hard time visualizing this, first of all, go to the lecture notes or the lecture slides, which will have a much better, be a drawing, it'll be a proper computer drawn like graph. But then extend this a few more, like in the same, draw yourself an interval L over here and extend the wave pattern a little bit further, see what you find, that kind of thing, and count how many full wavelengths you get in a various repetition. So drawing it in L is sometimes challenging to visualize. You can draw it beyond L if it helps you create a mental image in your head. We know what the relationship between the geometry of the instrument and the wavelength. And the key thing here is that the length of, as you notice, this is the length of one key. This is the length of the third key. And as we move kind of to the left along the instrument, the lengths get bigger. So the wavelengths can get bigger because the lengths are getting bigger. So what we can do is replace these wavelengths here, 2 times the length of the E key, and 2 times the length of the G key. The 2's cross off. What we want to solve is the length of the G key. So that's just a bit of algebra at this point. So we find that the length, if you know the length of one key, basically, you can just take the ratio of the frequencies and multiply it by the length of the key you know, and you get the new one. So again, I'll leave this for you guys. The calculator bit would probably, if you want the answer in centimeters, you can leave the length of the E key in centimeters. And it's useful at this point just to kind of really quickly inspect and make sure the actual final number on your own. But notice that these 2 hertzes, they'll cross off. So all we're left with is centimeters. The final answer that we want is, we want something in units of length, so we need to get centimeters or meters, kilometers, or something like that out of this. The only unit we're left with is centimeters. That's kind of a first great check that we passed. The other thing is, look at this fraction here. It will be less than 1. You have a number of about 1,300, and it's divided by a bigger number. So this fraction will be less than 1. So that means that this number that's less than 1 will be multiplied by 10. In other words, big key will come out shorter. This makes sense. We put a relationship down like this. It says as the frequency goes up, notice that the frequency here of the G note is higher than an E note. For the velocity or the speed to remain constant, something else has to come down. The wavelength should be shorter, and the wave is related to the length of the key, so the length should be getting smaller. This being less than 1, this kind of all passes a secondary check. So if you guys were solving this on a test, you could kind of rest assured that you did it correctly. Okay, so what is the phase speed of the waves in the key? That's pretty simple. We know the speed is related to the wavelength and the frequency. So since we have numbers up in kind of right here and here for the E key, and we don't need to calculate anything for G, we can just solve this. We could really use any note that truly exists on this scale, but we have all the information. The E is the easiest. So the wavelength is just equal to 2 times the length of the E key. The frequency is still just the frequency. And at this point, we kind of have everything we need. If we don't want speed in meters per second, it might be nice to, or sorry, if we want it in meters per second, excuse me, not centimeters per second, it would be good to convert the centimeters into meters. And we have 1318.5 hertz. So you guys can plug that one in too. Like I said, it's fine, but there's a lot of calculator work. I felt it was probably just easier to save us a bit of time on this one. But again, this is in meters. Remember that hertz means per second, the units that are going to come out of this. Meters per second are the units we're looking for speed, so it's all good. Okay, so I think this is our last question. I haven't noticed anything in the chat from you guys, so I assume that means I'm doing okay and you guys are understanding, and that's hopefully what we're all here for. So problem 4 says consider a water well with diameter of 2 meters and a total depth of 20 meters. So let's label this. I'm going to at least do it temporarily in variables. We'll use capital D for depth, and the diameter, we have this handy drawing on the right-hand side here, is lowercase d. So to determine the amount of water in the well, the frequencies of 2 standing wave modes in the well were measured. Standing wave modes were found at 28 and 39.2 hertz, but not in between. What is the volume of water in the well? So this is the kind of thing, I think it's a little ambiguous what's actually going on here. So if you guys were in person, I don't know what things will look like when you do come back in a week or two. But there's a lab where you do something very similar to this. The idea is that there's a speaker and you can adjust the frequency of the sound coming out of it. There's also a microphone, and you can measure if a standing wave is formed. You'll get a bit of resonance, the volume will increase, that kind of stuff. So the idea is that imagine you start at 0 hertz and you've got a dial and whatever's controlling your speaker, and you increase, and then you get to 28 hertz and you notice there's more sound coming out. You keep turning up the dial. Maybe you found some stuff in here, who knows what happened there. But at 39.2 hertz, you found something out as well. And there was nothing in between. So like in this region, no standing waves. No increase in volume, no kind of resonance is the proper term. Nothing in between. Maybe you could pretend that in this region here, your speaker wasn't sensitive enough, your microphone wasn't sensitive, so it's just not reasonable to do the experiment in that region. But the point is, here you have consecutive standing waves. So this is the first mode, or sorry, not the first mode, this is a mode. And then this is the next one. So they're consecutive standing wave modes. So using this information, we're trying to find out what is the volume of water in the well. So first of all, what type of standing waves are we dealing with? I kind of already spoiled this earlier. You could imagine, and this is not to say that it does not travel through water, that kind of thing, but what we're measuring is, and this is kind of often the challenge is setting up the problem, we're measuring the sound waves that are in the air. So they can vibrate inside the well in this space, but when we get to a much more dense medium like water, it serves to effectively attenuate all the vibrations. So we can consider that this is kind of a node and this is a fixed end condition. And if we were at the fundamental mode, these are probably higher than the fundamental mode, at least one of them is, but the fundamental mode would look something like this. So this is a fixed end condition at the water, but free kind of at the mouth of the well. So we've got the fixed free set of end conditions. And what we find here is that lambda is equal to 4L 4L3, 4L over 5, so on and so forth. And the general term is 4L over n for n n odd, n greater than 0. But we're going to use n in a second because there's not enough letters in the alphabet, so I'm going to erase that, just generally speaking. Okay, so where do we want to start? Okay, so what we know is I'm going to call this first one the mth mode, the m mode. We don't know what it is, so we're going to give it a variable m. It might be the 5th, it might be the 7th, it might be the 9th, who knows. And we're going to call this one n, and we're giving them two variables, and it will be important that we remember that m is less than. Okay, so we can write down speed is equal to the wavelength times the frequency for both the m case and the n case. And keeping track of the m's and n's will be very important, and I'm not off to a good start. Okay. We want to write in what is the length in terms of the geometry that we're working with. So it's 4L over m times the frequency. And we can also do the same thing over here, 4L over n times the frequency. But because we know the relationship here, right, between the harmonic numbers, this actually means n is greater than m, so equal to m plus 2. We can sub that in right here, and suddenly we don't have to worry about two variables. And the reason that we can do the plus 2 is because we know they're consecutive. So this is, if m is 5, then n has to be 7. If m is 11, n has to be 13, that kind of thing. And we can set these equal to each other, of course, by keeping them separate any longer because they're both equal to the same speed. So on the left side, we have 4L divided by m times Fm. That's equal to 4L. What we would normally write is divided by n, but we're going to make this substitution. We have Fn. So all we need to do now is we solve for m, and then I think we're good to go. So the four L's both go away. We have m2 is equal to, I want to do this, is equal to m times Fn divided by Fm. Yeah, so this term here in the brackets, Fn over Fm, this is greater than 1. Because remember, this n, the frequency is higher as we kind of define things. So what we'll do is we'll move 2 equals, yeah, this will be okay. And then we'll just factor out the m's and divide through by whatever factor is left. 2 is equal to Fn over Fm minus 1 times m. In other words, m is equal to 2 divided by Fn over Fm. So this all looks kind of wacky and like what's going on here. Let's actually solve this. I think the math is pretty simple. I kind of have this written down, so I'm not just amazing at mental math. If we fill in what the ratio of these two frequencies is, you take 39.2, you divide it by 28, what you're left with is 1.4 minus 1. It becomes 0.4, and the whole thing, you take 2 and you divide it by 0.4, you get 5. That's going to give us our first clue as to what these orders are. So we're starting to understand the problem, and we can start putting this together. So at this point, we're basically all set. It might not seem like it, but we can solve this problem pretty straightforward. So now that the point that we needed the m for, what was our harmonic number? Because we need to solve for what L actually is. L in this case is the area where the sine wave is happening, or kind of the linear region, and L is this bit. So now that we can figure out what L is, then we can figure out, we have the depth, capital D, we have L, if we can solve for that, then we can figure out what, let's just label this H, for instance. We'll be able to find H. And the volume of water is just equal to, this is a cylinder, it's a well, the circular area is pi d squared over 4, multiply that by H, and that's how we're going to find this volume of water. So really what we're trying to get at is H. We're given D, we just have to work really hard with some of this wave stuff to figure out what L is, and from L we can work out everything we need to know. Okay, so we have M. Let's revisit this equation. So the speed is equal to 4 times L divided by M, which we now know, times the frequency M, which we were given in the problem. That's 28 hertz. Also very important too, once we figure out what M is, as long as we don't need anything to do with M, like let's forget about this, we'll forget this, like 28 is the number we want, and we need to keep track of that because it's associated with M. If we start mixing the 39 and the 28, we're going to be completely lost. Okay, so we want to figure out what L is. Let's just do some quick algebra to get at that. So L will be equal to M, which is the harmonic number, which we solve for. That's 5. It's not the mass. Sorry if that's confusing. Like I said, we don't have enough letters in the alphabet. Divided by 4 times the frequency. And it's safe to assume, I think you guys should check whatever value. If you're writing a test, it will be kind of on the front page. But a good value for this is the speed of sound in air. This is almost always, we use 343 meters per second, I think, but you guys should check if you're using a slightly different value in this course. So at this point, the length is equal to, the harmonic number is 5, The speed is 343, we're assuming that, but it's a very safe assumption. It will change a little bit depending on the temperature, the humidity, that kind of stuff. So you might see values as low as 330, as high as 350, but nevertheless, it's okay. We've got 4, just a geometric factor, and the frequency, which I made a point of saying had to be 28, not to be confused with anything else. So at this point, I'm going to stop with I don't know what this is. You guys will put it in your calculator. You'll figure it out. The units look good on this. The hertz and the per seconds will probably just be left with meters. So at this point, we'll have we'll have L. We can compute H is equal to D minus L. And once we have H, we can plug that in, and we're all set. So I think that's that problem is, for all intents and purposes, it's solved. It's not, I haven't given you guys a final number, but if you guys are feeling up to it, you can totally on your own. So I think we're done about 10 minutes early, but I think that's all I have for you guys tonight. I'm happy to take any questions you guys, like I said, seemed like you were getting it, but I can hang around for a bit, and if you have any questions, I'm happy to take them.